Applications using exponential functions typically involve growth and decay, and our example here is one of growth. We have a bacteria culture growing with a constant relative growth rate, and the bacteria count is 400 after 2 hours, 25,600 after 4 hours. This should seem reminiscent of something you've seen in previous math work, where you're asked for an expression for the number of bacteria after T hours. That's part C. Part D, the number of cells after 4.5 hours. That should kind of make sense here. One thing you wouldn't have seen before is part E, find the rate of growth after 4.5 hours. When we see rate of growth after 4.5 hours, we should be thinking derivative. This is calculus after all. So looking at this through the lens of calculus, I want to unpack this constant relative growth rate part. Mathematical experience indicates that, and that's another way of saying, after you've taken enough math, you kind of see what the wording means. A constant relative growth rate really means that the growth rate is proportional to the size of the population. So it's constant relative to the population size. And now we're going to unpack this a little bit. The growth rate is proportional to the size of the population. We're going to turn that into a proportion equation. Growth rate. Thinking about things in terms of calculus, the rate at which the population is growing. So that would be the change in population as time changes, and so dp dt is equal to the constant of proportionality times the population size. So this growth rate is proportional to population size directly translates into an equation that says dp dt is equal to kp, where k is a constant of proportionality. Now what we have here is something that we're going to see in a later section of a different chapter that's called a separable differential equation. I don't want those words to get in your way here. Really think about things in terms of separable, and what we can do is we can separate this into things that contain p and things that don't. In other words, we can divide both sides by p and end up with dp divided by p, and then first derivatives act like fractions, so I can actually multiply both sides by the differential dt. So we end up with dp over p is equal to k dt. And now I'd like to find out what the function p is. And since we have differentials on both sides, we're going to go ahead and integrate. So on the left-hand side, we have the natural log of, don't forget the absolute value of p. And on the right-hand side, we have the integral of k dt. dt tells me that my independent variable is t. And so the derivative is kt, and then we need our constant. So kt plus c. In order to isolate p, because it's in a natural log, we can exponentiate both sides. So we use the base e, and we end up with p is equal to e to the kt plus c. Now that plus c as an exponent really translates into a product, e to the kt times e to the c. Because if ever you multiply numbers that have the same base, we add their exponents, right? Since c was a constant of integration, e to the c is also a constant. And thinking about the fact that t is the input variable, we could express what we've just written as p of t is equal to e to the kt times e to the c. If we let t equal 0, we end up with p of 0, which we're going to refer to as p sub 0, the initial population. Since in our expression e to the kt times e to the c, if we let t equal 0, e to the kt is 1. That means that p of 0 is equal to e to the c. That's the thing we're going to call p sub 0. So we can finally say that p of t is equal to p sub 0 e to the kt. Whereas we said p sub 0 is the initial population, and k is the rate of growth, and it is a percent expressed as a decimal. So looking through this lens, we'll now go back to the information that was given to us in the exercise. The bacteria count was 400 after 2 hours and 25,600 after 6 hours. So we can express that as when t is 2, population is 400. When t is 6, population is 25,600. Using our p of t equals p sub 0 e to the kt, we can rewrite this information in two equations. When t is 6, we have 25,600. So replacing 6 for t, we get 25,600 is equal to p naught e to the 6k. Likewise, when t is 2, we get 400 is equal to p naught e to the 2k. I'd like to know what k is. And in order to find it, well, look, we have a system of equations and it's got two unknowns, k and p sub 0. Fortunately, we also have two equations, right? The most painless way I can think of to isolate k is first to get rid of p naught. And since the second equation that we wrote, 400 equals p naught e to the 2k, has only one term on each side, we actually can divide the first equation by the second equation. On the left-hand side, 25,600 divided by 400 is going to give us 64. On the right-hand side, p sub 0 divides out, and we end up with e to the 6k minus 2k. We're dividing, so we subtract the exponents. So 64 is equal to e to the 4k. Applying the natural log to both sides, we get natural log of 64 is equal to 4k, which means that k is equal to 1/4 of the natural log of 64. Now, folks, if this was 1/6 of the natural log of 64, I would absolutely make it the exponent. 64 to the 1/6 is 2. Everything would be beautiful. 1/4 as an exponent on 64, nothing nice is going to happen. I'm not going to bother. And in fact, I'm just going to leave it there for now. We can flesh out just a little bit more our equation, though. We can say that p of t is now equal to p sub 0 times e to the 1/4 natural log of 64 t. I know, it's a little cumbersome, and there's another way to do it, but we'll look at that in just a minute. Looking back at the initial information that we were given, we were told when t is 2, p is 400. Therefore, we can say that p of 2 is equal to 400, and that's p sub 0 e to the 1/4 natural log of 64 times 2. We can now use this equation to find out what p sub 0 is. So 400 is equal to p sub 0 e to the 1/2 natural log of 64, multiplying 2 by 1/4. Now, that 1/2 as an exponent on 64, that's 8. Because that 1/2 as an exponent on 64 means square root. And folks, e to the natural log of 8 gives us that 400 is equal to p sub 0 times 8, which means that p sub 0 turns out to be 50. I liked keeping k in terms of the natural log because it gave us an exact answer for p sub 0. We didn't have any round-off error. But at this point, I think it would be appropriate for us to say that k as a calculator value is approximately 1.0397. With that in mind, we can flesh out the equation fully. P of t is equal to 50, that replaces the p sub 0, e to the 1.0397t, where the 1.0397 is the relative growth rate. But that's a decimal. Expressing it as a percent means that it's about 104%, which is huge for a population. The world's population grows at a rate of, 1 to 3%, somewhere around there. So 104%. If this is bacteria, you're not going to be doing very well. Further, we can say that the initial population size was 50 bacteria. Now, folks, with exponentials, logarithms, not everything's going to turn out to be a whole number. But if you're giving me a count of bacteria, please round to a whole number. Nobody has a third of a bacterium. Now, let's go back and see what we were asked for. Wow, that's a lot of writing. What is the relative growth rate? Express your answer as a percentage. We did that. What is the initial size of the culture? We found that. Find an expression for the number of bacteria after T hours. We found that. Let's parse this out. So the relative growth rate, that's part A, about 104%. Initial population size, that's part B, about 50 bacteria. So let me circle those. And then the population after time T, that's our P of T is equal to 50 times e to the 1.0397 T. And so we found those by accident just by exploring the information that they gave us. Isn't that amazing? Now, I'm not going to bother you with part D, finding the number of cells after 4.5 hours, or when the population will reach 50,000. You can evaluate those. But we will look at part E, which is find the rate of growth after 4.5 hours. In other words, we want dp dt when t equals 4.5. And dp dt, also known as p prime, is going to use rules we have for differentiating an exponential function together with the chain rule. And so the derivative of the inside function comes out as a factor. So 1.0397 times 50 times e to the 1.0397 t. And when we evaluate that at t equals 4.5, we simply replace t by 4.5 in the exponent. And that's pretty straightforward. Putting that into our calculator gives us approximately 5595. And this was a rate of growth. What we're counting is bacteria. We were told the time is in hours. And so that rate is bacteria per hour. A couple of notes here. Because we're counting living things, bacteria, this should be rounded to a whole number. And another thing is sometimes I put a problem like this on a test and folks don't use any calculus. They don't process that a rate means a derivative. And so just keep in mind, if you're taking a calculus test, you should probably use some form of calculus on the problems on that test.